Let's review simple linear regression. So in our analysis of an association, we pretty much come back with a binary response. Are the two variables related, or does it look like those two variables are independent? And if it does look like there's a statistically significant relationship, then we'd like to go further and actually try to describe what that relationship looks like. And with both x and y are quantitative numerical variables, we use simple linear regression to do our best to describe how the difference in y values seems to depend on differences in individuals' x values. So our model is as follows. Basically, our model says that the average value of y among all individuals in the population at a particular value of x is given to you by the equation of a straight line, the intercept plus the slope times that x value. So the model says that the average value of y essentially has a linear relationship with x. And we go a step further and actually describe how individuals' values of y behave. An individual's value of y is basically equal to the overall average value of y at that value of x, beta 0 plus beta 1 times that individual's x, plus a random disturbance. And this disturbance just represents the fact that not all individuals, of course, have the same y value as the average. They deviate by random amounts here. So we call beta 0 and beta 1 the coefficients of the model, and we would like to estimate those coefficients based on a set of data that we've collected, because these two coefficients help to describe exactly how the average value of y and x vary together. All right, so one key note about the philosophy of modeling, this is the model that we're going to use to approximate the relationship between x and y, but we know that all models are wrong. Some are useful. We're just hoping that this model is close enough to reality that we can learn something interesting about the relationship. All right, so the key thing is to know how to interpret the coefficients of a regression model, particularly the slope, but the intercept is there because a line needs an intercept, so it's worth talking about. The intercept in a simple linear regression beta 0 doesn't tell us anything all that interesting. We say that the intercept beta 0 is the average value of y when x is equal to 0, basically the average y value of all individuals in the population who happen to have x is equal to 0. Now, of course, this is rarely important unless x equals to 0 happens to be a particularly interesting quantity. Usually all x's are of equal importance, but like I said, a line needs an intercept. All right, the slope is what really ties the x and y values of individuals together. And so this is what we need to make sure that you know how to interpret. When we have a slope for a simple linear regression, what does that number tell us? Well, it tells us that two individuals whose values of x differ by 1 unit, they're expected to differ in y by beta 1 units for whatever reason. So it looks like actually my framed expression right here is slightly incomplete. This should say two individuals whose values of x differ in 1 unit are expected to differ in y by beta 1 units. So for whatever reason, remember it's not a cause and effect sort of thing going on. If beta 1 is positive, then the individual with the larger value of x is expected to have the larger value of y. If beta 1 is negative, the individual with the larger value of x is expected to have the smaller value of y. All right, one key thing to remember about a regression equation is that it's not a physical law like what you might study in, say, physics class. So E equals mc squared relates the energy and the mass of a particular individual together. This equation describes the amount of money you'd have in a bank account if you started out with a 0 amount of money and it was continuously compounded at an interest rate r after time t. So these two equations do describe physical laws. Basically, if I were to increase the interest rate of the bank account, that's going to make my amount in that account go up faster. But regression equations don't work that way. Regression equations do not describe what happens to an individual when they undergo change. The slope is just telling us how we expect the y values of two different individuals to differ when they happen to differ in x by 1 unit. So it never tells us anything about what happens to a particular individual's value of y if we could change his or her x value by 1 unit. That is beyond the scope of a regression model. That's the job of a physical law, and regression isn't a physical law. All right, so we've looked at this example before, the relationship between the salary at a company and the number of years of education of that employee post-high school. And it might be the case that our regression equation is that salary equals 4843 plus 128 times education. So what do these two numbers mean? The intercept just tells us the average salary among employees who have 0 education post-high school. Not a particularly interesting number. The slope is what ties salary and education together. And so what we can say is that two individuals that differ in x by 1 unit, they're expected to differ in y by the slope units. So putting that into the context of the problem, two employees that differ in education by 1 year are expected to differ in their monthly salaries by $128, with the more educated employee expected to have the larger salary since this is positive. So make sure you can interpret the slope and the intercept of the simple linear regression equation, because that's the key step in moving beyond a simple analysis of an association, saying yes or no whether or not there is an association, to actually describing exactly how x and y are related. All right, so how do we actually get these numbers? Well, there's literally an infinite number of lines that we could try to use to model this relationship. And we're just going to choose one of those. And the line that we're going to choose is going to be the one that fits the data the best. But I put the best in double quotes here because there's a particular criteria that we use to determine what makes a line better than others. So it makes overall broad sense to try to minimize the amount of error that the line makes. And we encode the amount of error that a model is making by talking about points residuals. So the residual of a point is just the difference between the actual value of that individual and the value predicted by the regression equation. So the residual, which is just the error that the model is making, is the difference between the actual value of y for an individual and the predicted value from the equation. And what we use to determine those coefficients is the least squares criteria. Basically, out of the infinity of possible lines we could use to describe the relationship, we choose the line who has the least sum of squared errors, essentially. The line that minimizes the sum of squared residual, sum of squared errors, over all points in the data set. And we do this because of classical reasons. It makes the math actually work out really easily. We could come up with a line that minimizes the absolute value of the residuals, but back in the day, this criteria actually made the math just really easy to work with, and so that's what we stick with. All right, so a note on notation here. Here's the model that we're using to approximate the real world here, that essentially if we had a census data on every single member in the population and we fit the least squares regression line, we would measure beta 0 for the intercept and beta 1 for the slope. So these represent essentially wholly quantities, the truth that we would like to know. But we're not going to know them because we only are going to have a sample. We're not going to have a census. We only have a small set of individuals that we've collected data on. And so when we find the least squares regression equation on the data that we've collected, we denote the intercept and the slope by B0 and B1 to make the distinction clear that these are just our best guesses, our estimates of what beta 0 and beta 1 are, the truth. And the upshot is that actually, our estimates will be pretty close to the truth, and we're going to expect them to be off by maybe a standard error or two. And we can make confidence intervals to come up with a range of plausible values. All right, so after we've determined the least squares regression line, really the first question to ask is this regression statistically significant? And basically another way of asking is, does our regression model help to predict y any better than the naive model? So what's the naive model? The naive model just predicts each individual's value of y as the overall average value of y in the data. And so we want to make sure our model's doing better than that, essentially not using any sort of information about x at all. And so what do? We compare the sum of squared errors when we use the naive model to the sum of the squared errors when we use the regression. So here's a scatter plot showing the points x and y values together, and we see a nice positive trajectory here. The naive model says, all right, I'm not going to use any information about x at all, and for each individual, I'm going to predict its y value to be just the overall average. So this horizontal line here represents the naive model, the overall average value of y in the data, and so it's making that prediction, that exact same value for every individual. And so we can look at the error that the naive model makes, basically the distance of the actual values of y with the value predicted by the naive model, square that error, sum that up over every individual, and it turns out we get a sum of squared errors of 1264. All right, well, what if we use the regression to predict y instead? So when we find the least squares regression equation, now we can look at the error that the model makes for each point, basically how far away each point is from the line. We can square that error, sum that up over all individuals, and it turns out we get a sum of squared errors of 174. So because the regression has more flexibility, we can tilt this line. It's not a flat horizontal line. It's always going to fit the data better than the naive model. We need to make sure that it's doing significantly better, essentially. So any predictor, even one that's unrelated to y, is always going to give a reduction in the sum of squared errors relative to the sum of squared errors of the naive model. We need to make sure that the reduction achieved by our regression is large, unlikely to produce, just by chance, from a regression predicting y from a completely unrelated predictor here. And so that's what we're going to use to gauge the statistical significance of a regression. We're going to measure the reduction in the sum of squared errors when we go from using the naive model to predict y to using the regression model to predict y. There's always going to be a reduction. We need to make sure that reduction is large. Okay, so here's the formality here. We're going to say that the reduction in the sum of squared errors of our regression model is statistically significant if it's unlikely that this reduction, or a reduction even larger, would have occurred just by chance. In other words, if we tried to predict y from a regression using an unrelated predictor, or had x and y just been unrelated here. So what we can say is that the regression is statistically significant if it predicts y better than the naive model, essentially just predicting each individual's value of y to be the overall average, and it predicts better than a regression using a predictor just unrelated to y. So how can we tell what values of the sum of squared error reduction occur by chance? Well, we can once again run the permutation procedure. Take the observed values of x and y that we have in our data and randomly pair them together to make a permutation data set. By design, x and y are unrelated in that permutation data set, so we can find the least squares regression line and calculate the sum of squared errors that that line achieves and compare that to the sum of squared errors of the naive model and see how much a reduction happened essentially by chance, since x and y are unrelated here. Do this many, many, many times, and we're going to say the p-value of the regression is the fraction of those permutation samples that just so happen to achieve at least as large a reduction in the sum of squared error as our regression. Or in other words, the p-value of the regression is the probability that at least as large a reduction in the sum of squared errors would have happened by chance by using a regression with a predictor unrelated to y. And so if that p-value is less than 5%, we say that it is statistically significant. It's unlikely that we would have been predicting y so much better than the naive model just by random chance. So we've looked at this simulation here. Here's the relationship between salary and education. The red line is our least squares regression line. And to determine whether or not our regression is statistically significant, we want to know, well, okay, do we predict any better than the naive model? And do we predict any better than, predicting salary from a predictor unrelated to it? And so this envelope of gray lines represent the regression lines observed over the course of running the permutation procedure, randomly pairing up salary and education so that there's no relationship between the two, and then finding the least squares regression line from that. So in a sense, anything that looks like one of these gray lines inside this envelope is a line that is reasonably likely to occur just by chance, if education didn't have any information about salary. And so what we notice is that the line that we actually measure from our data looks significantly different. It's steeper, and so it is somehow different than what would happen by chance, and so we would say that this regression is statistically significant. Now, looking at it the other way, in terms of the the prediction accuracy of the sum of squared errors, over the course of the permutation procedure, we keep track of the reduction in the sum of squared errors of each of these regression lines on the permutation data sets relative to the naive model. And over the course, these are the distribution of the sum of squared error reductions that we get essentially just by chance, since each one of those permutation data sets is predicting salary from a predictor that's completely unrelated to it. So these are the values of the sum of squared error reductions that happen by chance. Here's the value that we actually observed, highly out of line, much bigger than what happens by chance. So once again, we can say that the regression is statistically significant. It's definitely it's predicting much better than the naive model, just predicting the overall average value of y for each individual, and it's doing better at predicting salary than some predictor unrelated to it. Okay, so our overall rule for significance is looking at the p-value and seeing if it's less than 5%. If it's less than 5%, we say the regression is statistically significant. The reduction in the sum of squared errors that it achieves is unlikely to have arisen by chance, had we predicted y from just a regression using no information about y at all. And so that's all that it says, is that reduction is unlikely to happen by chance. Remember that a statistically significant regression may not be particularly useful or indicate a really strong relationship. We always check these other measures, r squared and the root mean squared error, to assess the practical significance. So on the other side of the coin, if the p-value is at least 5%, we say the regression is not statistically significant. Essentially, the reduction in the sum of squared errors we get when we use the regression is about the same size as the reduction in error that we get when we predict y using a predictor unrelated to it. So nothing impressive. Doesn't mean there's no relationship going on. It just means it's so weak that we couldn't detect it. There might be a lurking variable involved. There might be no relationship. We're not sure. But we just don't see any statistically significant relationship. So when we use R to actually get the p-value, we're actually going to assume that the regression model is an appropriate reflection of reality, namely that the distribution of the potential disturbances of individuals, how far away from the regression is well described by a normal, to actually get the p-value without running a simulation just to speed things up. But the interpretation is the same. All right, so when we look at a summary of the model, we get the following output from R. And it's going to be your responsibility to be able to talk about pretty much every single number that you see here. So one thing that we're curious about is whether or not the regression is statistically significant. What's the p-value of the regression? Right here, bottom right-hand number. In this case, less than 5%, so we know this regression is statistically significant. To gauge the practical significance, we can look at the r squared of the regression model, which R refers to as the multiple r squared, about 17%, meaning that we get about 17% of the way there to knowing y by using our model. Basically, we get 17% of the way there to knowing salary if we know the individual's education. All right, the root mean squared error, essentially the typical size of the residual or the typical size of the error made by the model, R refers to as the residual standard error, and it's $433.4 in this case. The equation of the line can be found by looking at the intercept and the slope. The intercept is in the column labeled intercept, in the row called intercept here, and we see it's 3.2 to 8.83. The slope is in the column labeled estimate in the row labeled after the name of the predictor variable. So the slope is a little over 85 right here. Okay, so with a simple linear regression, those are the quantities that we talk about: the intercept, the slope, the residual standard error, in other words, the root mean squared error, the typical size of the residual, r squared, and the p-value of the regression. Now, since we know that these coefficients are just estimates of beta 0 and beta 1, we might like to know, well, how far off is my estimate likely to be from reality? That's what this standard error value is. The one last value you need to know is this value in the standard error column in the row named after your predictor, and this is telling you the standard error of your slope. Basically, we realize our slope is just an estimate. We know it's going to be off from the truth by some amount. This is a pretty good guess for how far off our estimate is likely to be from the truth. Beta 1, had we had a census and fit the least squares regression line with every individual in the population. All right, so how do we recover the regression equation from this output? Well, this is our value for the intercept, and this is the value for the slope. The equation for the regression line is that the predicted value of y is the intercept plus the slope times x, so we just fill in the numbers. So the estimated salary hat, is equal to 3228.83 plus 85.39 times education. So make sure you know how to do that as well. All right, a bit more about the root mean squared error. This is a very important number when talking about the regression model. And the root mean squared error tells us the typical size of the residual. In other words, how far away points are from the line. And another way to think about it is that the root mean squared error is the typical size of the error made by the regression model, the typical difference between what the regression is predicting for y and what the actual y values in your data set are. So what makes a large value of RMSE and a small value is open to personal interpretation. So I can't quite give you a great guideline for that. But looking at the root mean squared error is key to determining whether or not your model is going to be useful. The root mean squared error tells you essentially how close your predictions are getting to the actual values. And if that number feels large to you, then maybe that regression isn't all that useful. The second measure is r squared for looking at the practical significance or utility of a model. And the r squared of the model is interpreted as follows. Basically, we say that r squared gives the percentage reduction in the sum of squared errors when we use the regression model to predict y rather than the naive model, the overall average value of y. So in other words, we can more informally interpret it by saying, using your regression model gets you 100 r squared % of the way there to knowing the value of y. So back a few slides, we saw the naive model and the regression model for predicting y. This is the sum of squared errors from the naive model. This is the sum of squared errors using the regression. And basically, the r squared value is the percentage reduction in the sum of squared error when we go from the naive to the regression. So there's a very large reduction here. The percentage reduction relative to the naive model is that value of r squared. Okay, so larger values of r squared are better, but once again, there's no hard and fast rule for how big an r squared needs to be for the model to be useful. And also, a very large r squared isn't necessarily indicative that the model is appropriate to actually be using to model the relationship. It might be the case that we have a nonlinear relationship with a large r squared. So you always got to confirm that your regression model is an accurate enough reflection of reality to use. So how do we do that? Well, all of the formulas that we talk about, all the numbers from the output, confidence, prediction intervals, etc., are only going to be trustworthy as long as our regression model really is a reasonable reflection of reality. Essentially, an individual's y value is given to us by the location of that regression line plus a random disturbance, and the possible values of those disturbances, how far the individuals might be, is well described by a normal distribution. So what does this translate to when we actually look at our model? Well, we need to look at the scatter plot and the residuals plot to make sure the trajectory of the stream of points is actually well described by a straight line. When we look at the scatter plot, we make sure that the vertical deviations up and down from the line are about the same everywhere. We don't want to see some values of y where points are tightly clustered around the line, other places where they're more spread out. That's a violation of the assumptions. And then also we need to make sure that the differences between the regression line and the actual values of the points, overall they're well described by a normal curve. When that's the case, then regression is an adequate reflection of reality and we can use the results. So graphically, what does that mean? Well, here is an example of the regression model holding exactly. Basically, here's our scatter plot of y versus x. And basically it says, all right, let's take a small slice at a particular value of x and look to see what the individuals values of y look like. So they're scattered around the line, and if I look to see at the distribution of that scatter, the distribution of those residuals, I see that it is essentially peaking at 0. The y values are peaking exactly at where that line is predicting, and it has some amount of width here, and this width is the same everywhere. The amount of deviation up and down from that line is the same regardless of the x values of the individuals, regardless of the y values of the individuals, etc. So basically it just says that if I take a small slice up and down at any particular value of x and look at the deviations of individuals' values from where the line predicts, you're going to find a normal curve, and that normal curve looks the same everywhere. So when that's the case, the remarkable thing is that we can actually predict how far off our estimates are likely to be from the truth. So that standard error of the slope, which we mentioned a little while ago, gives us a measure for how far off our estimated slope is from the sample, how far off it's likely to be from the truth, beta 1. And so we use this information to come up with a confidence interval, essentially a range of plausible values for the truth based on the data that we've collected. And the logic behind this was as follows. It turns out, and you can see this with the simulation, that for about 95% of random samples, their slopes that you measure using the least squares estimates turn out to be at most 2 standard errors away from the truth, beta 1. So it stands to reason that if we take just the slope from the one sample that we have and go plus or minus 2 standard errors, that range of values, that interval, should have about a 95% chance of covering the truth, actually getting it right and having beta 1 be inside it. So for more confidence, we have to include more values, so we have to go a little bit more than plus or minus 2 standard errors. But that's the general rule for 95% confidence, and that's what we usually stick with. And so, in general, an approximate 95% confidence interval for the truth is taking our point estimate and just moving plus or minus 2 standard errors. So what do we mean by confidence? Well, if we come up with a 95% confidence interval for the truth, say between 55 and 72, we say we're 95% confident that beta 1 is between these two values. So what does being confident mean? What does being 95% confident mean? Well, what it means is it's referring to the long-run fraction of time that our procedure actually ends up getting it right. So we'll never know if a particular confidence interval contains the truth or not, because the truth will forever remain elusive to us. But we know that in the long run, 95% of these 95% confidence intervals we end up constructing will end up containing beta 1. The only issue is we never actually know which ones do. We just know in the long run, beta 1 is going to be inside there 95% of the time. All right, so when the assumptions look to be true, when regression is a reasonable reflection of reality, not only can we come up with a confidence interval for the true slope, beta 1, we can also come up with confidence intervals and prediction intervals for new individuals to kind of figure out what their values of y are. So there are two types of prediction. We might be interested in predicting the overall average value of y among all individuals with some particular value of x, basically trying to predict mu of y given x, or we might be trying to predict an individual's value of y who happens to have a value of x here. We'll denote that by yp. Now, our best guess is just plugging in that value of x into the regression equation and doing the math to get the predicted value. And it's the same predicted value regardless of whether we're predicting the overall average or an individual's value of y. Now, how far off we think those predictions are from the truth depend on what we're trying to predict. So if we're trying to predict the overall average value of y at a particular value of x here, here's the formula for the standard error, and we gain some interesting insight about how it worked. Basically, the more scatter that we have in the stream of points, the worse fitting our model is, the larger the root mean squared error is, the more uncertainty we're going to have in our predictions. That makes sense? The larger the data set we have, the larger the value of n, the smaller the standard error of our predictions are going to be. That makes sense. With more data, we've kind of nailed down our estimates to a much higher precision. Another insight was that the farther that the x's were spread out from each other, the larger the standard deviation of the x's, the more certain we are in our estimates, the smaller the value of the standard error. And perhaps the most important insight, the accuracy of our predictions, basically the amount of uncertainty we have, depends on how far the value of x at which we're making our prediction is from the overall average value of x in the data. The amount of error that we have, the amount of uncertainty we have in our predictions grows when we make predictions farther and farther away from the overall average value of x. All right, so if we're making a prediction about the overall average value of y among all individuals who share some common value of x, we say that that interval is a confidence interval. So we're 95% confident that mu of y given x is inside the interval. If we're talking about a particular individual's y value, we call it a prediction interval, and we say that there's a 95% chance that the individual's y value is in the interval there. So slightly different terminology depending on what we're trying to make a prediction for, and make sure you are clear about when confidence and prediction intervals are used. One thing we do have to worry about when making predictions is extrapolating. So extrapolation occurs when a prediction is made outside the scope of the model. So one example of extrapolation would be trying to predict what would happen to an individual if his or her x value changes, because the regression model isn't designed to actually make a comment about that at all. And another type of extrapolation is when you try to make a prediction at a value of x that's outside the range of x used to build the model. So the predictions are trustworthy as long as we're making that prediction at a value of x that the model's essentially already seen before. And we can kind of confirm that, yeah, it looks like my model's a good reflection of reality there. If we make a prediction at a value of x that's far outside the range of x values used to build the model, well, there's really no guarantee that the fitted relationship is going to continue outside, the range that it's already seen. If we make a prediction at that value of x that's far outside that range, then we're making the additional, really unwarranted assumption that that relationship is going to continue to have the same form at this unseen value of x. And we don't want to take that risk. It might be the case the prediction turns out fine, but there's no guarantee that it will. All right, so confidence intervals, prediction intervals, all these things rely on the regression model being a reasonable reflection of reality. And so one of the key things you always need to do is to make sure that the regression model really does seem to adequately reflect reality. So we need to make sure the relationship between x and y is linear enough. We need to make sure that the vertical spread of points away from the line is essentially the same everywhere. There aren't some values of y or x where points are tightly clustered around the line and others where they're kind of spread out. And we need to make sure that the residuals as a whole, how much individuals are deviating from the regression line, have a distribution that's well described by a normal. All those intervals are incorrect if the model's not really a good reflection of reality and we can't trust them. So our main tool is to look at the residuals plots. Basically what we do is we look at the size of the residual. Remember, the residual is the vertical deviation between an individual point and the regression line. It can be positive or negative if it's above or below the line. So we look at the size of the residual versus the predicted value of y, basically the location along the regression line. And what we want to see is no interesting patterns. If we do see any sort of interesting pattern, that means there's some aspect of the relationship between y and x that isn't being captured by a regression model. And that's a bad thing because your regression model is supposed to explain everything there is to know about the relationship between x and y. So good residuals plots would look something like this, where we don't see any sort of global curvature away. We don't see areas where residuals are mostly positive, mostly negative, or anything like that. It's an even mix above and below zero everywhere. It doesn't matter about the horizontal clumpiness at all. We can see kind of gaps in the residuals or kind of where residuals are concentrated on the left or on the right. That's just an artifact of the particular x values in the data set, not about the relationship. We just care that there's no obvious curvature in the stream of points and that the deviations, the sizes of the residuals, are about the same up and down everywhere we look from left to right. So these are great. These show some very obvious violations. There's some very painful curvature in the residuals plot, indicating there's something left over in the relationship that our model hasn't explained. Here we have that the sizes of the residuals are very small for small predicted values of y, and the sizes of residuals are typically a lot bigger at larger predicted values, and so that's a violation of the assumption. We assume that they're about the same distance, about the same size, no matter where we look from left to right. And here we see another example, very obvious curvature as well. So these are what we don't want to see. That implies our model's inadequate. One thing to be careful about is that our mind is really, really good at identifying very small, kind of inconsequential patterns. So the only violations we care about are really typically painfully obvious. You have to ask yourself, hey, is that a little curvature I see? Or, hey, is that spread a little bit unequal? Chances are that pattern's not severe enough to really mess up our estimates all that well. Deal-breaking violations are typically very painfully obvious. All right, so we can use the residuals plot to check the equal vertical spread and the linearity assumptions, but the normality assumption we require the QQ plot. So we can look at the histogram of residuals to see for some vague resemblance to a normal distribution, but the better plot for this is the QQ plot, which compares the size of the residual versus the size they should have been had the residuals been coming from a normal distribution, one of those bell curves. And so we want to see the points inside the upper and lower dotted bands, with the exception of maybe a few points on the far right or the far left, because that indicates good concordance with a normal distribution. So this would be a good QQ plot. I'd be happy with seeing this. I would not be happy with seeing this QQ plot because I see this global systematic curvature away. I see a lot of points outside the upper and lower dotted bands on the left and the right, and even a little dip in the middle here. That's indicating a systematic departure from normality, implying the normality assumption of the model is incorrect, implying that all those confidence intervals, prediction intervals, all that's wrong. The model's not an adequate enough reflection of reality to use. So there are statistical tests, and we're actually going to start by looking at the statistical tests of the assumptions, but we're not going to be too worried if we fail them, because we already know our model is wrong, it just can't be too wrong to use. So failing these tests, tells us nothing new, it just tells us our model is wrong. Our goal is to make sure that it's not too wrong to use. So we'll always start out by looking at the results of the statistical test, and if we pass them, hey, we're good to go. And these tests work a little bit differently than the p-values we've been discussing before. Typically, we want to find a statistically significant association. That's an interesting result in business analytics, to find two variables that have a relationship. And so we like seeing p-values less than 5% because that indicates something interesting is going on. Now, for the test of regressions, we don't want to see the p-value being 5% or bigger. When the assumptions, the test of the assumptions, have p-values of, sorry, I might have botched that, I already forgot what I said. What we want to see are p-values 5% or bigger. Now, why is that? Well, the regression model is supposed to explain all there is to know about the relationship between x and y. Getting a p-value 5% or bigger says that there's nothing interesting left over. Basically, you've done your job. You've explained all there is to know. If that p-value is less than 5%, then the assumption is violated. Basically, there is something interesting left over, and your model hasn't explained that, and that's a bad thing. So we would like to see p-values of 5% or greater. That means from a statistical point of view, our model is adequately reflecting reality well enough. So our overall strategy, look at the tests first. They'll probably be failed. If they are failed and you don't have very many data points, 25 or fewer, stop. The model's not good enough to use. If you have more than 25 points, look at those residuals plots, the QQ plot, to make sure the violation isn't too severe. Small violations are okay. What do we do when we do have violations and we can't use the simple linear regression model? Well, what we can do is approach the problem from a different angle. So the regression model just says an individual's y value is beta 0 plus beta 1 times that x value plus a random disturbance. But there's nothing about the regression model that says that x and y have to be the quantities that we originally measured in the data set. So we could call x and y, say, the distance and the amount of money that someone's spending at a store, but we could also call x and y to be, say, the logarithm of the distance that people live from the store, and say y be the square root of the amount of money that people are spending. It doesn't matter really what x and y are, they just have to be numbers. So they can be what we originally measured, or they can be transformations. So sometimes it can be the case that we can find a different way to measure the variables, basically, looking at taking the variables and raising it to some power, or taking logarithms, where the relationship between those transformed quantities actually do have a linear relationship. And then when we can do that, we can get an intercept and slope out for those transformed variables, and then untransform that equation using algebra to get an equation of the form y equals dot dot dot. So the last thing you need to know about simple linear regression is what to do when it goes wrong. And basically what we do is we try out a tremendous amount of transformations, look at measuring the variables differently by raising it to a various power or looking at logarithms, and then choosing the model, choosing the set of transformations that seem to fit the data the best. And based on that set of transformations, we can write out a linear regression predicting y trans from x trans, and then use that information to go back to our originally measured variables, y and x, and rewrite the equation in the form y equals dot dot dot. So you can look at the homework examples and previous exams to see some examples of the kind of algebra I'll expect you to do. So that wraps it up for simple linear regression. And we want to start adding more predictors in our model for a few different reasons. One thing that we know is that simple linear regression can give a very naive description of the relationship between x and y when there are lurking variables. So if I'm looking at the relationship between salary and education, the regression line might actually give a misleading impression of how the two are related if there are other important factors for why individuals differ in their salaries. So we need to take into account lurking variables before really describing the relationship between our variables of interest within the equation. Multiple regression will allow us to do that. So let's head there now.